Okay, so welcome to Lesson 1, Physics 12 online. So we're going to start looking at work, power, and efficiency. It's the first lesson out of Chapter 3. So some of this stuff should be review for you guys. I know Physics 11 was a while ago, so let's review some of this stuff. So, work, one of the definitions that you guys would have had for work at some point is this idea that work is the force on an object times how far that object is displaced. So we've got work equals force times distance. This idea of power, you would have looked at power at some point. The idea of power is that it is equal to work divided by time, change in time. And how efficiently you do something, or this idea of efficiency, is how much. Well, in this particular case, we're going to talk about efficiency as it's related to power or energy. So, in the context of power, efficiency is how much you've used divided by how much was made available. So that'll give you a fraction, a decimal. Generally, when we talk about efficiency, we consider percent efficiency. So we're going to multiply that by 100, and that's going to give us percent efficiency. There we go. That's a little hard to read. Percent efficiency. So as you can see here, although work depends on two vector quantities, so force is a vector, displacement is a vector. We don't generally treat them. That got worse. We don't treat work itself as a vector, and the reason for that is the mathematics behind how we multiply these two vectors together. Generally, we just kind of make it's kind of hand wavy. For those of you who've done IB math already, the reason I write it like this is because work is actually the dot product of force and displacement, which you would have looked at in your vectors unit in IB math, if you have looked at that already. So, for those of you who haven't looked at IB math, don't worry about it. We're just going to assume, for the time being, that work equals force times distance. There's some other versions of this equation. So if you look at, if you've done IB, the equation that you're going to be familiar with is this idea that work is equal to F, your force as a vector, dot your displacement as a vector. And so that's going to be one of the expressions you would have seen for the dot product is that the dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between him. Now, if you look at this, you'll see that the angle between the force and displacement, because they're parallel to each other, the angle between them is 0. Cosine of 0 is 1. So we can see here that when the force and displacement are parallel to each other, that disappears, and we have the expression that we used before. Work equals force times distance. So I'm just going to box this over here. I'll make a note. This is IB. Again, if you haven't taken IB, don't worry about it. It'll work out. This is also what you'll see in Physics 111, wherever you end up taking that, assuming that you go off into physics next year. One of the other formulations for this idea of of work, is that work is defined to be change in energy. And so we get this equation here. The amount of work that goes into something is equal to the change in energy. This, again, triangle is delta. So that is going to be the energy at the end minus the energy that was present at the beginning. This here is an F minus energy initial. So I'm going to see if I can actually zoom this in, maybe give you a better read on what's going on here. Okay, so work, the idea behind the reason we do work is that produces some form of energy transformation. So maybe you put work in and you you give something kinetic energy, for example, or a friction force produces heat. So an applied force, generally the applied force is done by you. So this is, and you take food energy. Well, the form there is chemical energy. And by applying a force, you turn food energy into kinetic energy. Or perhaps friction acts on something. Friction acts on a moving object. Kinetic. Taking kinetic energy and generating heat. Heat is another form of energy. Or gravity. We get this idea that potential energy or gravity takes, I spelled that wrong, potential energy and turns it into kinetic energy. Whatever this idea of potential energy is, we'll get to it here again in a second. So we get potential to, shouldn't have said energy, I'm sorry guys, it should be kinetic energy. So these are definitions of work that you would have seen, hopefully, grade 11. Again, that was a long time ago for you guys, so if you need to review some of that, let me know. I can go over that for you. So power here, let's keep going. Power is how quickly you do the work. So your average power is the amount of work you do divided by the time. So we get P equals W over T. And if we look here at what this expression has for us, we can look at some of the units here. So power is measured in watts. You can see that here, named after James Watt, a physicist who, or a scientist who lived in, I want to say, like the 1800s. But if we look here, we can see, so if power is measured in watts, work, the units for work, well, we have a few things. We said, first of all, that work was equal to force times distance. Well, that means we've got newtons times meters. Well, we have watts over here. My units are in pink. So we've got the work, W, is given to us as newton times a meter. But we also said further up, here, that work was equal to a change in energy. Well, energy is measured in joules. So work, the units for work are going to be given to us as Newton meters, or they'll be given to us as joules. And time is always given to us in seconds. So this idea of the watt is that watts are joules per second. Or, if you look at what's going on here, you have this idea of the joule is equal to a newton times a meter. So that gives us another expression where you have an expression for power where you have newton meters per second, which is going to give us another equation that we're going to work with here in a bit. If you look at these units right here, you'll see that joules equal to a newton meter. We have newton meter per second. Well, meter per second, that's just a velocity. And a newton is a force. So that's going to give us our last expression here for power. One of the other expression that we can now have for power is this. Power is equal to your force times the average velocity of your object. And so we'll look at some of the applications there. So on the page here, the last concept we're going to look at here is this idea of efficiency. Efficiency is given to us by this Greek letter. I believe it's eta, as it says right there. It's used to represent efficiency. So this little guy here, I'll write it bigger for you. It's kind of a fancy N. So this eta, again, is one of the expressions we had for it was use power divided by available power. Another way to think of it is the output, how much you actually do, divided by the input, what was made available to you to start. So let's do an example that uses all of this. So we have a 250 kilogram mass lifted at constant speed of 2 meters per second for a distance of 12.5 meters. We want to find a few things. We want to find the work done. we want to find the required power. We want, and if the motor is using 10 kilowatts of electrical energy, we want to find the efficiency. So we're going to put all of these concepts together here, hopefully in a way that makes sense. So free body diagram, first of all, always. Let's draw what's going on here. We have let's assume it's a box. The thing weighs 250 kilos. We are told that this thing is being lifted at a constant speed. So constant speed means acceleration is 0. What that means is the forces on this thing have to be balanced. Well, there's 2 forces acting on this thing. One doing the lifting, and, well, this is on Earth, so we've got gravity. So we've got Fg acting downwards. Fg is going to be, again, mass times gravity, which is going to be 9.8 times 250. Which is going to be 2,450 newtons. But again, constant speed means acceleration is 0. If acceleration equals 0, that implies that F net equals 0, which implies that my forces up equal my forces down. Which means that the applied force upwards, Fa, is going to be 2,450 newtons. So let's, I'm going to record some of the other information that we've got here. So that's my free body diagram, but we also know a few other things. We know this thing is moving upwards. It's got an acceleration of 0. It's got a velocity of 2 meters per second. We're told that it's lifted 12.5 meters. So we need a few things here. So this is all the information that we've got. Let's go through and look at how we can solve this problem. I think, here, give me 1 sec. I need to wipe my... Does that make anything clear? No, maybe not. I'll see. Okay, so here we go. First of all, we want to find the work done. So part A, work, we had a few expressions for it. The easiest one that we can use is force times distance. Work equals Fd. So we know the force acting on this thing. We know it's 2,450 newtons. We know that the distance this thing was lifted was 12.5 meters, so we get an expression for the work. 2,450 times 12.5 is going to give me 30,625 joules, or 30,625 Newton meters. Again, you have to have units, but again, we've got options for the units, so I don't particularly care which one you choose to use. I want to make sure I can keep all of this on the same page here. So let's look at B. We are told to find the required power to actually make this happen. So, expression for power. We have work already. So if we look back at the expression we had for power that involved work, power was equal to work over time. So we've got the work. The work was 30,625. The time, though, what is the time required for this thing? Well, if we go back and look at this thing, I've got a couple pieces of information here that are useful. I've got a constant velocity, and I've got a displacement, or distance traveled, 12.5 meters. So we can actually use an expression from kinematics to solve this thing here. So we know that the time is equal to the distance an object travels divided by how quickly it travels that distance. So we're told that it traveled 12.5 meters at 2 meters per second, which is going to give us a time of 6.25 seconds. So we can use that now to figure out what our power is. We know 30,625 joules of work was done, divided by 6.25 seconds. So we're going to get an expression for power here of 4,900 watts. But, just so you can see what else is at work here, no pun intended, we had another expression for power. Power, we said, was equal to my force times my average velocity. We've got those things here already. The force acting on the object was 2,450. And this thing's moving at 2 meters per second. Well, I've got my force there, times my average velocity, which we're told was 2. And this should be clear to you guys. 2 2,450 times 2 is going to be 4,900, which is exactly what we expected it to be. So we can use either equation here to figure this thing out. So there's A, there's B. Let's go over here and take a look at C. Let's slowly slide this thing down here. Question C. If you got your books in front of you, you'll see that it's asking for the efficiency. We're told that the motor is using 10 kilowatts of electrical energy. Find the efficiency. So I'm going to slide this down here a little bit further. We need to zoom this out. Sorry, that's getting a little blurry. So we've got efficiency. Eta. No, I gotta zoom this back in. Sorry, guys. Efficiency eta is given to us as the output divided by the input times 100. So my output, how much energy was, or how much power rather, was actually used, that's 4,900 watts. That was the output given to us. But how much was put in? We are told in the question that the motor itself was a 10 kilowatt motor. And so what that means is this. Well, first of all, let's go back up here. Sorry, guys. 10 kilowatts. 10 kilowatts is 10,000 watts. So that tells us how much power that motor is using. So we've got the output. Actually, I should put this down here. Sorry, guys. Equal efficiency equals output over input. So my output was the 4,900 watts that was actually done, divided by the 10,000 watts that went in, and we're going to multiply that by 100. And what that's going to give us is an efficiency of 49%. And believe it or not, that's actually pretty good from a motor like this. It's your standard run-of-the-mill motor. Cool. So let's keep going. A couple more examples to go over. Yeah, a couple more examples. Let's pick this up. So we want to recall some stuff. Recall work done by an applied force changes chemical energy into mechanical energy. So your energy that you've taken in gets converted to mechanical energy. This object is moving. So let's take a look at what this looks like. Let's do an example here. So in general, a force in the direction of motion does positive work. A force that opposes motion does negative work. Is how we is the convention that we use here. So if my object's moving to the right, this force here is doing positive work, while this force here is opposing the motion. It's taking energy out of the system. So we say that this thing is doing negative work. So important to note that although work can be positive or negative, it's not a vector. It has no direction. It's just whether or not energy is going into the system or energy is coming out of the system. Work, again, is defined as, I'll write this down here, change in energy. So here's an example for you. A 10 kilogram mass is pulled across a 3 meter long floor that has a coefficient, that's a coefficient of friction there, guys, of 0.1. And the force that is doing the pulling is 50 newtons. We want to see if we can figure out the work done by the pulling force, the work done by friction, the total work done, and the efficiency. So for body diagram, here we go. We've got a box. The box is on the ground. The box weighs 10 kilos. So let's look at the forces acting on our block. It's on Earth, so we have a force of gravity down. Fg is mg. So the force of gravity here is going to be 98 newtons, 9.8 times 10. This ground is level. It won't always be, but this ground is level. So because it's level, we know that the normal force is equal to the force of gravity. They're equal and they're opposite. So this is going to be 98 newtons. We are told that there was a 50 newton applied force pulling on this thing, so I'm going to put that to the right. 50 newtons applied. And there's going to be a force of friction that opposes this motion. Force of friction equals mu Fn. Oh, sorry, guys. Force of friction equals mu Fn. We had a mu of 0.1, and an Fn of 98, which is going to give us a force of friction of 9.8 newtons. We're told the floor is 3 meters long. So there's the distance this thing is traveling. So it's going to be relatively straightforward. Work done by the pulling force is going to be the force itself times how long or how far it pulled rather. So 50 times 3 is going to be 150 joules or Newton meters of work done. That's A. Part B here, the work done by friction. My work is equal to my force times my distance. Now the force is acting to the left. The motion is to the right, so I'm going to call that direction positive. So my force here is negative 9.8 because it's acting opposite the direction that my object's moving in. And it's going over 3 meters. So the work done by friction is going to be negative 29.4 joules. So the total work done is exactly what you might think it would be. Work total is equal to the sum of all the work. Work. Sum of work. So I've got 150 joules minus 29.4 joules. That means my total work done is 120.6 joules. Or another way we can think of it is because work total is equal to the sum of the work, we could look at it this way too. Work total is equal to F net times D. And what we could have done if we'd wanted to is to say, okay, well, my F net is 50 minus 9.8 times 3. And we would have gotten the same result there. 120.6 joules. So now we can look at the efficiency. We've got the total work done, the amount of work that was actually done. This is the amount of work that our applied force put in. So let's look at efficiency. Efficiency is output over input. How much work was actually done divided by what we put in. So we know 120.6 joules of work was actually done divided by the 150 joules of energy that was available to it. If you do the math there, you're going to get that this thing is basically 80% efficient, and that there should be a 6. Cool. So let's do one more example here. I'll zoom this out so you can see the whole worked problem. So I've got my force of friction over there. I've got my applied force there. These are the two things that are doing work. Cool. Okay, flip the page. Here we go. So we looked at objects like this before. We've got a lawnmower moving a distance d. Let's take a look at the free body diagram here. So it's a lawnmower. Let's put wheels on it, make it actually look like a lawnmower. The forces that are acting on this thing are as follows, as you guys probably, hopefully remember. We're on Earth, so we've got force of gravity acting straight down. This thing is on level ground, so my normal force is acting straight up. Lawnmowers generally move left and right, not up and down. So we're told, and are we told here? It's being pushed forward. This force here is acting this way. So what that's actually going to end up doing, if you've ever mowed the lawn, is it's going to create motion this way. So I've got my forces here. We got one more force. Generally speaking, there will be friction acting backwards. Force of friction. So that's it. These are my forces. Fn, Fg. I'm going to zoom this in here. Sorry, guys. My force of friction. And this applied force here, F. That's my free body diagram. Now I'm going to break F up into its components. You've got an Fy acting downwards, and you're going to have an Fx acting forwards. Fx, there's no Fy. Now, we said that work was equal to force times a distance. One of the things that is important to recognize here is it has to actually move in that direction. So this thing's moving forward. It's not moving up or down. So we can look at a few things here. We know the work done by the normal force is 0. It's not moving up. The work done by gravity, is also 0. It's not moving down. And the force of friction here, this is going to be negative work. Well, the question is, what here is actually doing work? The Fy component that's pushing the lawnmower down into the ground, but the lawnmower isn't dropping, so there's no work being done here either. But what is going to contribute to the work is this Fx here. This guy's going to give us positive work because the lawnmower is moving to the right, and that force is acting to the right. So work equals force times distance. Well, the force that's acting, the work done by F, make a note here. This is work done by the applied force. This does not take into account the friction. So this is going to be Fx times the distance, but, well, Fx is just, if you look at your trig, Fx is F cos theta. So then we're going to get F cos theta times d, but that's just FD cos theta. So now we've got the expression that I gave to you guys right at the beginning of this lesson. I'm just going to skip down to the bottom of the page. This is a rather interesting result that we quite like here. No, sorry, I want to zoom that back in. Move this thing over. No, I can't do that. Sorry, I gotta do this way. Is that work is equal to FD cos theta. The force has to be parallel to the work done. Be like this. Okay, one more example, and I'll leave you guys for the lesson today. So flip to page 152, or take a look at page 152. That's example 6 right here. We're doing a lawnmower question. So let's take a look at this. This will be a good review. Free body diagram. I've got force of gravity acting down on a 100 or a 15 kilogram lawnmower. That's going to be mg, mass of 15 times 9.8 is going to give me a force of gravity of 147 newtons. I'm going to have a force upwards. It's going to be a normal force. I don't know what that is yet. I know it's upwards because the ground is level. And this is one of the things that we struggled with last chapter. Do not put a value here for Fn yet. The reason for that is because we have other forces acting up and down. Specifically, we have this Fy component here. So Fy, do we know what yes, we know what the applied force is. That's 80 newtons. We're told that in the question. So then this Fy here is going to be 80 sine 32. Oh, slide that over here. Sorry, guys. Which is going to give us a value for, actually, I'm just going to leave it like that, 80 sine 32. And then I'm going to have an Fx here. That's going to be 80 cos 32. And then there's one more force acting on our object. We've got the force of friction backwards. Well, the force of friction depends on the normal force, so let's actually take a look at what the normal force is. This is where mistakes were made. We have a Fy down, and we've got an Fg down, but the object is not moving down. So that must mean my normal force here has to balance Fy and Fg. So Fn is going to equal my y component acting down plus my gravity component acting down. So Fn is going to be 80 sine 32 plus 147, which is going to give me a value of, for my normal force, of 189.4 newtons. So I can use that to find my force of friction. We are told that the coefficient of friction between the lawnmower and the lawn is 0.12. Again, there's no units here. Coefficient of friction is 0.12. So my force of friction is going to be mu Fn, which is going to be 0.12 times 189.4, which is going to give me a force of friction of 22.7 newtons. And last but not least, so that is now my completed free body diagram. Direction of motion is to the right rather. So you want to know the work done by the applied force and the work done by friction. So here we go. We've got the work done by the applied force. The work done by the applied force is going to be the work is going to be equal to my force times my distance times the cosine of the angle between them. This F cos theta is just Fx. If you look here, there's my F and my cos theta. So we're going to have 80. Do we know how far this thing moved? We know that this thing moved 6.75 meters. So 80 times 6.75 times the cos between my force and the displacement, so that's 32 degrees. That's going to give me a work done of 457.9 joules, again, or Newton meters. That's A. And then B, what is the work done by friction? Work done by friction is just going to be, in this case, if we look at this, friction, where is it? Friction's right there. Is parallel to my direction of motion. So I don't have to use this cosine expression. I could just use FD. Just to be consistent for this particular question, I'm going to show you what this looks like with the cos theta expression in there. So my force of friction is backwards, so it's going to be negative 22.7 times the 6.75, and then I'm going to have the cosine of 0. If you put cosine of 0 into your calculator, you're going to get that cos of 0 is actually 1. So then we're going to get the work done here is going to be negative 153.41 joules. And if we wanted to, we could go and do the exact same thing we did in the last question, find the total work done and find the efficiency. But I'm not going to do that here. You're going to do that as part of your homework. So that's it. That is the end of this lesson. If you've got comments, questions, concerns, my office hours are going to be tomorrow. I'm going to flip the page here. I'm going to give you your assignment. List of questions I want you to do. This is the same list that I gave you in the doc in our Google Classroom. So the exercises I want you to look at here are 1, 2, 6, 8, 10, and 11. So take a look at that. Hope you guys have a good day. I will be posting more of these as we go.